Okay, thank you everyone for joining the Athena seminar series. Today we have Raghav Pothukuchi. He's an associate research scientist at Yale University. He is an NSF CRA Computing Innovation Fellow with Professors Abhishek Bhattacharjee, also of Athena, and Jonathan Cohen of Princeton. He received his PhD in computer science from the University of Illinois at Urbana. And his research is on brain-computer interfaces, quantum and classical frameworks to accelerate cognitive models, and biologically inspired computer architectures. He also has interdisciplinary work on building intelligent and secure computer systems using control theory and machine learning. He has been selected as a young researcher at the Heidelberg Laureate Forum, and he has many honors and awards to his name. So with that, I will introduce Raghav.
Thank you, Rajeshi, for the kind introduction, and thank you all for attending this talk. Now, one request, in addition to the technical comments and feedback, I'd appreciate if you have feedback on the overall nature of this presentation as a job talk. I'm going to use this as part of my faculty candidate interviews. So I'd appreciate any comments regarding that aspect. So with that, thanks again for coming to this talk. What I'm calling here the infinite brain refers to systems that can connect to the brain and replicate its function. Such systems have been variously called as the digital brain or the electronic brain by Alan Turing, or the cybernetic brain by the cybernetician William Gray Walter. I'm a computer architect, and my vision is to build systems that can connect natural intelligence with artificial intelligence. In this presentation, I'm going to share why I think that's a goal worth pursuing and how my research towards that goal has led to this virtuous cycle of innovation of developing computer architectures and systems for the brain sciences, and use the challenging constraints from that domain to stimulate the design of new computer systems. Realizing my goal requires building machines that can read the electrical activity of neurons in the brain, decode their underlying thoughts, memories, transfer them to external servers if needed to replicate cognition, and communicate with the brain directly using electrical feedback. Such systems can help, for example, an individual with Alzheimer's to store their declining thoughts and memories. Better, it could help that individual arrest that decline and hopefully lead a normal life. Such a system can also help a healthy individual by augmenting their cognitive capabilities. For example, it could allow them to process the vast amounts of information across the entire internet just with their thoughts, much like an infinite brain. In the past, we have seen how such a vision for machines has led to key advances in computing, and in fact was instrumental in shaping some of the early discoveries in this field. In 1945, Vannevar Bush described a hypothetical device called the MEMX. The MEMX is a device that can store all the information records in the world, but can easily find what we are looking for using brain-like associative recall. In a few years, William Gray Walter became the first to surgically implant electrodes in the motor cortex of paralyzed individuals who could use them to advance slides on a screen projector just with their thoughts. Walter, along with their colleagues, laid the foundation for cybernetics and the computational modeling of the neuron. This, combined with insights from the brain sciences, led to the emergence of machine learning and AI. And in this zeitgeist, prominent architects were interested in building machines that were inspired from the brain. These machines have since come to be called computers. Since those original ideas, much has happened. Today, we are able to develop brain-computer interfaces, or BCIs, that can read and stimulate thousands of neurons in the brain. And we can even safely surgically implant them. The bottleneck are systems that can process the exponentially growing volumes of data that these devices can now sense. Similarly, we have cognitive and AI frameworks that can at least partially replicate brain function. And these frameworks are in an increasing need of computational support. Fortunately, we're also well aware of the tremendous progress in computing and computing technologies. Now is the time to leverage that progress to build new computer architectures and systems that can deliver the necessary performance per watt to advance our understanding of the brain, replicate its function, and be able to communicate with it. And that has been the goal of my research. My work began with the HALO project. HALO is a multi-accelerator BCI processor that can interface with one brain region. I helped make HALO real. Building on this work, I designed Scalo, which is a wirelessly networked distributed system of implants that can interface with multiple brain regions. I also worked on systems that are far from the brain, but which are necessary to help replicate cognition. And this include Distil, a compiler that I developed for cognitive frameworks written in high-level languages like Python. Distil allows these frameworks to run on multi-core CPUs and GPUs, providing orders of magnitude faster performance and thus enabling the use of more complex cognitive models. Now, some of these cognitive models can be computationally hard. So I also explored the possibility of using quantum systems to run them. I developed Quattro, which is a collection of cognitive models that I mapped to quantum computers. Using these applications, I identified the research necessary for these emerging accelerator systems to support cognitive model. An important aspect of building these distributed systems that process large volumes of data is the intelligent orchestration of data and compute. And I worked on a number of techniques towards that goal. Some of these come from the brain itself, and the others come from control theory and machine learning. Now, all of this work has this synergy of building computer architectures and systems on one side and helping the brain sciences on the other side. And this synergy has led me to innovate at multiple layers of the stack, making contributions to computer architecture and system design, and providing new generations of tools and platforms to the computational brain sciences. My BCI work demonstrates the design of new distributed multi-accelerator systems. Distil is a new application of domain-specific compilation, and Quattro is being integrated into emerging cognitive modeling platforms, thus presenting a new domain for quantum computing to target and uncovering new research in the area. And I demonstrated these contributions with a variety of artifacts. My BCI work has been taped out. Researchers at the Yale School of Medicine are planning animal tests based on these systems. Distil has been integrated into Sinulink, a modeling tool used in the cognitive sciences. Quattro is being integrated into Sinulink, and I'm also working on a community-wide effort led by Intel in upstreaming the new constructs that we have found with these applications to guide the design of future quantum systems. In today's talk, I'm going to share the highlights of some of these contributions, and I'm going to do that with the help of a target application. Consider the case where it is necessary to mitigate seizures that an individual is experiencing, and it is also necessary to restore complex cognitive function that has unfortunately been lost. This can happen, for example, in an individual with glioma, a type of brain tumor. Now, to mitigate seizures, we need systems close to the brain, like the brain-computer interfaces that can identify and interrupt those seizures. And to restore complex function, we need powerful computational frameworks, but which unfortunately cannot fit in the tight constraints of near-brain computing. Thus, we need systems that are far from the brain, perhaps, but are designed to run these frameworks. I worked on both these kinds of systems, but in today's talk, I'm going to focus mostly on BCIs and especially on Scalo. And then I'm going to briefly summarize the work that I've done on systems that help replicate cognition using computational frameworks. So beginning with Scalo. Scalo is a BCI, which is a device that can read the electrical activity of neurons in the brain, decode its underlying actions, memories, thoughts, communicate with external devices like prosthetics, servers, and the brain using electrical feedback. Such systems could be used as wearables placed on the surface of the scalp or be surgically implanted inside. My work has been on surgically implanted processors. Even though these systems have the most stringent design constraints and also pose the risk of surgery, they're used at the cutting edge of neurotech. The reason is that signals captured at the surface of the scalp are attenuated by 2 orders of magnitude. So surgically implanted BCIs are used in several applications. In the near term, they are being used to treat debilitating neurological diseases. There are many programs that are undergoing clinical trials for the use of BCIs to treat these diseases. Several of them have already received FDA approval. In the US alone, there are more than 15,000 individuals who use surgically implanted BCIs today to treat epilepsy. These are only some examples. There are many research programs that are exploring the use of BCIs to restore movement, treat acute depression, restore vision, restore speech, and improve memory. The WHO estimates that there are around 300 million individuals worldwide who suffer from the diseases of the brain and the mind. And an important fraction of these individuals are resistant to medication, meaning that surgery is their only option. So BCIs are here to stay and can make an impact. But there are also enormous computational challenges in building these systems. Now I'm going to present to you those challenges, beginning with the hardware that is used in these applications. A typical BCI system has the components that I'm showing here on the screen. There are the electrodes that are used to sense and stimulate neural activity. There are a variety of electrode form factors that have different processing rates that are used to collect these signals. The signals from these electrodes are then digitized and processed. My work has been at the processing layer. Then there are components for power and communication. All of these are integrated into a tiny hermetically sealed module which can then be implanted. Now, this module has stringent power and temperature constraints. This device cannot heat the brain tissue by more than 1 degree Celsius. Otherwise, it can risk damaging brain cells. Now, the safe amount of power under this thermal limit varies depending on the specifics of the implantation, but in my work, I've been targeting an aggressive limit of 15 millivolts. Now, this is for the entire package, meaning that the processing itself has about 5 to 10 milliwatts of power to run BCI applications. So here are the kinds of applications that the system should run. Now, there are many applications in this space, but I'll focus on two exemplars. One is seizure network detection. For a long time, seizures in the brain were thought to be localized to the regions where they occur. But recent neuroscience has shown that multiple regions of the brain, in fact, interact to trigger these seizures. And these networks evolve over time. So this requires distributed processing to identify seizures from multiple regions of the brain, correlate them to detect these seizure networks. Now, one way to do this analysis is perhaps to exfiltrate all the data to an external device. And this requires, for example, wires, but wires pose risk of infection and also limit the movement of the individual. Another option is perhaps to use wireless communication, but as I will show later, unfortunately, wireless communication offers a tenth of the requirements of processing the data that all these devices sense. So the preferable option is to process all of the data on device. And since these devices are power limited, as I mentioned in the previous slide, we need to be able to use multiple of these processing elements close to the sensors in a distributed manner to support these functions. Now, because our understanding of the brain and its diseases is incomplete, clinicians and neuroscientists use a variety of signal processing algorithms to understand brain signals. This is a non-exhaustive list of the kind of algorithms that are used in this field. And because there is a lot of variability between individuals, these algorithms are instantiated with various configurations and parameters across individuals. And the BCI must support all of this processing in real time. And this is only one kind of an BCI application. Another exemplar is movement intent decoding. This application decodes from the brain signals from different regions of the brain, the movement that the individual wants to make. You've seen an example of this application in a video earlier, but in that video, the data is being collected from only one region of the brain. In reality, there are multiple regions of the brain involved in planning and executing the fine-grained movements that we are capable of. This is also another application which needs to support complex signal processing within strict real-time constraints. So what I've showed you so far paints the picture of BCI design as a challenging distributed system design problem. The device must process large volumes of data from multiple regions of the brain, run it through complex signal processing, meet a real-time latency of a few milliseconds, and be flexible to personalize the device to individuals, adapt to changing conditions, and importantly, support the many algorithms that are being developed. And all of this must occur within stringent constraints of temperature and power. Existing devices are far from this ideal. They choose between interfacing with one or two regions of the brain, processing low volumes of data, or specializing to a single function. There are some devices that allow processing large volumes of data or use bespoke methods to interface with multiple regions of the brain. But they offload the data and computation to external devices and thus can have longer response times. Importantly, no device today supports the distributed processing on the BCI to support the needs of current and future BCI applications. I'm doing research to advance the state of the art. Scalo is such a system that is the outcome of aggressive cross-layer co-design. I begin by rewriting neural data processing pipelines to develop on-device distributed applications that are optimized for communication. I then design a processor that provides low power acceleration while being flexible to support many applications. Thanks to the unique properties of the hardware, which I'll go over in a few minutes, applications can be optimally scheduled using an integer linear program. And despite all this complexity, Scalo is easily programmable in high-level languages like MATLAB and TrillDSP. Scalo is a contribution to computer architecture with its unique cross-layer co-design to meet extreme design constraints. And it is also a contribution to neuroengineering because it's the first design that supports distributed on-device processing that can scale to several brain regions. Now, I'm going to walk you through the design of Scalo and show you how we realize these contributions. And I'm going to begin with an important consideration that we need to address in the design of a distributed BCI, and that is of communication. Consider seizure network detection. This application requires monitoring different regions of the brain for seizures, and when a seizure is detected, the data has to be broadcasted from one region to another region to check their correlation. Now, transmitting the data collected by a sensor in one region using state-of-the-art BCI radios takes about 25 milliseconds. This is too long, and we cannot simply speed it up by accelerating computation. So we need a way to rewrite the applications to filter the communication involved such that they are then amenable for distributed processing. And the technique we use to do that is locality-sensitive hashing. Locality-sensitive hashing is a technique that encodes a window of a signal into a hash of a few bits. The key here is that if signals are similar, they're encoded as the same hash. Now, this is somewhat different from conventional use of hashing, where we want because we want here the hashes to collide if the signals are similar and not collide if the hashes are different. So with locality-sensitive hashing, the data required to represent the signal is reduced by 2 orders of magnitude. And the effort required to compute the similarity is as simple as checking for hash collisions. So with locality-sensitive hashing, the seizure network application is refactored as follows. We have each device in Scalo monitoring its region for seizures. And at the same time, the signals are encoded into hashes, and both signals and hashes are sent to local storage. When a seizure is detected, the source broadcasts the hashes of all its data. And the remaining nodes in Scalo check if they collide with any of those hashes that were locally generated. If so, they respond back, and the source transmits only those subset of signals for which there was a hash collision. And finally, the remaining nodes run the full expensive signal similarity check for just this subset of signals. So this pipeline is now amenable for distributed processing with its reduced communication. If you look carefully, what we've actually done here is we've added computation to mitigate communication. Now, that might seem counterintuitive because the application, its real-time requirements and the hardware already seem to be over-constrained. But that is okay because we know how to build efficient architectures that can run this computation, and that's what I'm going to show in a couple of slides. We rewrite the movement intent decoding application similarly, but without the hashes to optimize for communication. In the original application, we need to transmit the data from multiple regions of the brain to run, for example, an SVM or a Kalman filter or a neural network to decode the movement. And as I mentioned earlier, this requires transmitting a large amount of data. Instead, we propose computing the partial outputs locally and transmitting only those because they are 2 orders of magnitude smaller in size and thus can complete in real time in a distributed manner. So here too, we have added computation to mitigate communication. So once we have redesigned our applications for distributed processing, we need to select an architecture that can efficiently run them. And this architecture needs to meet multiple objectives of performance, power, area, and reuse. And by reuse, I mean the flexibility to support multiple applications. Now, one obvious choice is a low-power RISC-V microcontroller. This is flexible because it's a CPU and can run any application, but it's not efficient. So an alternative is to use an application-specific integrated circuit, an ASIC or an accelerator. This is efficient, but it's not flexible. We want to support many applications. Now, what about using multiple of those ASICs? This could work and is in fact along the lines of what we ultimately do, but we have to be thoughtful about how we do it. Simply building one ASIC per application is not scalable. Ideally, we want to grow the number of new components we build much slower than the number of applications that we want to support. Now, building one ASIC per application is also uh, not reusable because, as I'm showing here on the screen, different applications like the seizure detection movement intent use signal processing kernels that overlap but in different configurations. Producing a new ASIC per application duplicates design effort and wastes area. Also, this is ineffective from the perspective of energy consumption. The applications have different stages and process different levels of data and compute. Building a single accelerator to run for the entire application means that we have to clock the entire circuit at the frequency to support the weakest link in the pipeline. And this wastes energy for the entire ASIC. So we come up with a new architecture where we make the accelerator as the primitive and build pools of accelerators supporting classes of functions. And we designed these accelerators, which we now call processing elements or PEs, modularly to optimize them for reuse and area. So let me give a couple of examples of what I mean by that. Consider the local seizure detection pipeline. You could spot here common signal processing kernels. And we could decompose this pipeline into those kernels and build accelerators for them. Now, by suitably buffering between these different processing elements, we can run each PE at the lowest frequency to be energy efficient. Now, it is not always so straightforward to build the PEs from these applications. Consider locality-sensitive hashing. There are different measures that are used to compare signals from different regions of the brain. Now, supporting hashing in hardware might mean we build a separate group of PEs for each of these measures. But instead, we identify that there is a common structure to this process of dividing the signals into windows, convolving them with a random vector, and counting consecutive n-grams in the convolution output. So with this observation, we had to design only 3 PEs, make them configurable to support various stride sizes, window sizes, and so on, and thus support hashing for all these measures and more. We proceed in a similar manner to design the remainder of the PEs in the system. And our PEs are configurable. For example, one could tune the number of points of the FFT or the bandwidth of the various filters and so on. We also include a RISC-V microcontroller to be conservative to support any application that does not have a matching PE. Now, the RISC-V microcontroller is also responsible for configuring the data flow between the PEs, but it is out of the loop for most of the execution. This means that the PEs can directly access resources like storage and network without the involvement of the CPU. Now, this avoids the orchestration overheads that are typically found in many conventional heterogeneous systems. And we compose all these PEs in a globally asynchronous, locally synchronous design such that we can tune each PE's frequency to the lowest value necessary to sustain application throughput. We have a configurable interconnect that can chain these PEs into flexible pipelines. And finally, we build the PEs to be predictable in their power and performance at various data ingestion rates, which facilitates deterministic compilation and scheduling. So at this point, I want to highlight the significance of what we have accomplished with this architecture. What we've done is we've refactored these applications for distributed processing, identified the recurring signal processing kernels in them, built hardware to run those kernels, and as I will show in the next slide, users can directly program these kernels. This is like building an instruction set architecture for BCI applications, but reimagining the architecture where we have the accelerator as the instruction. Of course, there are many ways to improve on what we've done. For example, one could use techniques from compilers and formal synthesis to identify the minimum number of PEs that we need to build as the number of BCI applications and use cases increase. And we could also, of course, automate that process. We designed most of the PEs manually in our design, but there are some PEs, for example, like the FFT PE, where we were able to use automated generation, such as from CMU's spiral generator program. Now, there is a lot of scope for innovation to extend such approach, this kind of an approach to the BCI landscape and thus simplify design effort. Now, with the waning of Moore's law, accelerator-based systems are here to stay, and the accelerator as the instruction philosophy is perhaps the way forward. Now, what Scala also shows is a new design point in balancing efficiency with flexibility. And the key to that has been to modularize compute and make the data flow and compute configurable. Now, third, Scala also shows a way to minimize CPU-led overheads. For a long time, computer architects have been building systems that try to bypass the CPU for accelerators to access resources like network and storage. Scala presents a new template in that design space. And finally, the hash-based communication used in Scala creates fast and slow paths that allow the design to scale, and this is broadly applicable beyond BCI, such as in IoTs and other cyber-physical systems. It is these insights that has led this work to be recognized with some of the top honors from the computer architecture community. So once we have built this architecture, here is the compilation stack. Compilation proceeds in three broad stages. In the front end, the high-level programs written by users in languages like MATLAB and TrillDSP are parsed to obtain a DAG of computations. This DAG is combined with the hardware configuration to formulate an integer linear program that is then solved to find the optimal mapping of tasks to all the PEs across the system. This is then translated to a C program that invokes low-level library functions to configure the data flow between the PEs, and this is finally compiled to obtain RISC-V binaries that are programmed onto the various nodes. So here is how everything fits together. We have the multi-accelerator BCI processor that we designed, and we integrate it into a node that has many components off the shelf or from prior work. These include a non-volatile memory to store the signals, hashes, and other information, radios to communicate between the implants, and radios to communicate to external systems, components for power delivery, and analog digital components to interface with various kinds of electrodes at various programmable rates. This is the node that can then be implanted, and there could be multiple such nodes. A clinician or a neuroscientist can program these devices using high-level languages to set up the various closed-loop applications I've been talking about, which can then run autonomously. We realized Scala with detailed physical synthesis at 28 nanometers and partial tapeouts at 12 nanometers. We evaluated using publicly available data sets collected from humans and animals. So now let me show you the highlights of Scala's evaluation, beginning with the scalability of communication, which is an important aspect of making a distributed BCI. So here I'm showing you the maximum aggregate throughput of communication plotted against a varying number of nodes and various per node power limits. When communicating signals, throughput scales poorly. This is because signals are big and saturate the network bandwidth. On the other hand, communicating with hashes scales much better. In fact, at around 60 nodes, communication with hashing scales is 3 orders of magnitude higher than that of signals. This shows that hashing is incredibly effective. Now, there's a natural question to be asked here. While hashing is effective, hashing is also inherently probabilistic. So what about hash errors and how do they influence applications? So here I'm showing the hash comparison errors on the y-axis for 4 signal similarity measures: cross correlation, dynamic time warping, Earth mover's distance, and Euclidean distance as a function of the distance between a pair of signals normalized from their similarity threshold. So the signals above this threshold are similar, meaning that a hash error in this region is a false negative, where the two signals are incorrectly encoded as different hashes. On the other hand, signals below this threshold are dissimilar. So a hash error here means that they're falsely encoded as the same hash. So this is a false positive. So here are the hash errors. Now this is a busy chart, so let me walk you through it. From the y-axis, you could see here that the fraction of errors is small. Second, you could see that most of the errors are concentrated near the signal similarity threshold, where the underlying measure itself is weak. Say we are talking about a cross-correlation threshold of 0.7 and the cross-correlation measured values of 0.69 or 0.7. You could also see that the errors are biased towards false positives. We do this on purpose by engineering the hash. The reason is that a false positive can be resolved by a subsequent full signal similarity check. On the other hand, what about this tiny fraction of false negatives? So here I'm showing the impact of those hash errors on the application measured in terms of the maximum delay in detecting seizure propagation. You could see here that unless the error rates are high, the impact on the application is small. The reason is that there is a lot of spatial and temporal correlation in the brain. Signals that are nearby a particular electrode capturing a seizure signature also carry the seizure signature. And signals in consecutive time windows also carry the seizure signature. So the error rates have to be really high to impact the application. And you could see here that we've been conservative with the design of Scalo. Now, how does all of this translate to the application performance? So here I'm showing application level metrics for the two exemplars. I'm going to compare Scalo's design with a design called Central that takes the data from all the regions of the brain and processes them on one node. Now, this in itself is an advancement over many state-of-the-art designs by providing flexible on-device compute. Now, compared to this design, Scalo can process one order of magnitude higher data. That is, the impact on the application is 10 times better. This is the regime where we begin to see the promise of these devices. And this is a contribution to neuroengineering. Researchers at the Yale School of Medicine are planning animal tests following these results. I'm going to talk more about it in my future work. So what I've shown you so far is that the BCI space is rapidly growing, but there are enormous computational challenges in building BCIs. Scalo is a design that advances the state of the art while innovating in the computer architecture and system design. Importantly, Scalo sets the stage for exciting new research to advance computer architecture and systems while also helping the brain sciences. Of course, I've only presented the processing aspect of a BCI design. In reality, many themes must have to come together to realize a wirelessly networked distributed system of implants. These include innovations in power delivery systems, communication, packaging, algorithms, surgical techniques, and more. But what we've shown with Scalo is that if these were to come together, we now have the capability to flexibly process all of that data on device in real time, and thus set up an incentive for, in fact, for all of these techniques to come together. The closed loop control of the brain is one of the most powerful engineering ideas in our era, and Scalo takes a big step in that direction. What I've shown you until now is the design of Scalo, a BCI that sits close to the brain and, as in our target application, helps mitigate seizures. Let me briefly walk you through the design of systems that are far from the brain, but which are necessary to restore complex cognitive function. These systems run what are known as computational cognitive frameworks. Processing in the brain is complex. Multiple regions of the brain are involved in processing a task, identifying the alternatives, sampling information from the environment, attending to the stimulus, integrating it, and making a decision. Cognitive scientists represent all of that complexity using computational frameworks with a variety of mathematical constructs. I developed a compiler called as Distill that can run these frameworks on multi-core CPUs and GPUs. But in this research, I realized that this may not be sufficient for the future. This is because these frameworks are getting increasingly complex. Today, cognitive models routinely use computationally hard constructs like simultaneous constraint satisfaction networks and even quantum probability methods. Now, the use of quantum probability in this context might seem a little odd, so let me take a brief minute to explain why. For a long time, cognitive scientists have been using classical probability to model human behavior. But for a long time, they've also known that human behavior violated classical axioms. For example, consider this study, which has since been repeated several times, where individuals were shown the statement on screen and were asked to select from one of the two following options. Surprisingly, more individuals selected the second option. And this is surprising because it is a conjunction of two judgments, whereas the first just had one. In classical probability, the conjunction of two events can never be likelier than either of those two. Now, with quantum probability that uses vector spaces and projections, this can be easily modeled. Now, this is only a simple reason why quantum probability has become an attractive tool for cognitive modeling. There are other reasons, such as the ability to model the inherent uncertainty of decision making and the ability to capture the effect of prior judgments on current decision making, all of which are resulting in quantum probability gaining rapid traction for cognitive modeling. Now, for the target application, we have a quantum decision making model. This model describes decision making as using a landscape of multiple potential wells. There is one well for each possible choice. And the parameters of the landscape are set based on values estimated from the individual's state of the brain. And the decision-making dynamics are modeled through a series of quantum particles with different amounts of energy that fall at various points in the landscape. The well that collects the most number of particles is the decision predicted by the model, and that information is then conveyed back to the brain. Now, to know where a particle falls in this landscape, we need to know the eigenstates of this landscape. So we have this eigenstate problem embedded within this cognitive model. And this model can become easily complex by considering the interaction between the particles and the interaction between the wells and the particles and changing landscapes dynamically, which is all reflective of natural human behavior. So the question is, how do we build systems that can allow these models to scale to the levels required to capture human behavior? Considering the nature of these computations, we are now forced to look beyond conventional accelerators, such as towards quantum computers, to see if there's an answer. Quattro is the outcome of that exploration. Quattro is a collection of cognitive models. I begin by identifying various cognitive models that span various aspects of decision making and include computationally hard constructs, including quantum probability. I map these models to existing quantum computers using a variety of quantum algorithms. I then run these on existing digital and analog quantum computers to study their performance and programmability. So this effort has resulted in contributions to computer architecture by identifying new research in this domain and new applications for quantum computing to target, and also a contribution to the cognitive sciences by presenting a new processing paradigm to support novel cognitive modeling. So now I will briefly highlight how we realize these contributions in the context of the quantum decision-making model in our target application. Quattro takes this eigenstate problem in this cognitive model and maps it to quantum computers using variational methods. Now, what are to be gained by mapping a well-known eigenstate problem with well-known variational methods? It turns out there is much of interest to the computer architect. A variational method typically operates on the principle that the lowest eigenstate of the landscape is the state for which it has the lowest amount of energy. So it has a parametric circuit with tunable gates whose parameters can be tuned to provide various candidate solutions. Then there is an array of components to measure the energy of those candidate states. And the energy components are all aggregated to obtain the energy of that state. And a classical optimizer tweaks the parameters of the circuit to provide increasingly better candidates. And this process iterates until the lowest eigenstate is found. Now, to find excited states as required by our application, there is an easy extension. This is to run this algorithm with multiple initial states, aggregate all of their energy into a weighted sum, and change the parameters of the circuit. We find, however, that this application runs poorly on existing quantum hardware. The reason is that the optimization function is complex and there are many serialization overheads. Instead, a better solution is to decompose the problem into subproblems that can then be run in parallel. Even though there is an overlap in computations, we can run all of them in parallel. But it is not enough to get a good algorithm. We need an architecture that can efficiently extract that parallelism and execute it. And that is what we find lacking with the help of Quattro. In today's quantum cloud, users need to manually specify the parallelism in these applications, such as the multiple excited states that we can run in parallel. And users also need to manually orchestrate the execution to realize the performance benefits of all that parallelism. These are performance and programmability challenges. I'm not going to go into the details of how we overcome these limitations. But at a high level, the gist is that we could leverage our vast experience in building classical cloud systems to come up with new schedulers and systems like cloudlets that can augment the performance and programmability of the quantum cloud. And that is what is required to help deploy these models in real time to operate with data coming in from the brain. Now, this is of course only one model. The other models in Quattro reveal other unique insights about system design. So what I've shown you with Quattro is that cognitive models can benefit from quantum computing, but there is research necessary to realize that potential. Quattro is a new application suite to guide that new research with a view to enabling real-time execution of cognitive models. And just like with Scalo, the work with Quattro is broadly impactful. Excited state problems, for example, are also common in domains like physics and chemistry. And even broadly, the systems research that we do can benefit many disciplines. This is the reason why our experience in building Quattro and the new research that we have discovered has made its way into a community-wide report on the future of quantum computing. What I've shown you so far are systems that are close to the brain and those that are far from the brain, working together to help realize a target application. Now, where do I go from here? The work that I've done so far marks a significant milestone towards supporting the needs of this target application. But there is a gap that needs to be bridged in providing a BCI platform that interacts with a heterogeneous cluster of accelerators that run powerful cognitive frameworks and which can be set up as a platform to enable clinicians and neuroscientists to advance their work. Bridging that gap is the goal of my future research. Last year, I was in the operation room to observe the implantation of a BCI in a patient. And the patient required electrodes to be implanted in multiple regions of the brain, but the device being implanted has the capability to process only 2 of them. In my conversation with the team, I was told that this is not unusual. There are many cases where users have, for example, 10 to 16 of these electrodes, each with 4 sensors that are implanted, but the device can process only 2 of them. So the remaining are all open looped in the head. If the clinicians need to change the parameters of the device, they need to perform another surgery. Now, this experience has taught me how vital it is to design these devices safely, ethically, and to maximize their functionality. Towards that goal, I've been working with clinicians and neuroscientists at the Yale School of Medicine to pilot the use of my systems in treating seizures from epilepsy and tumors and the effects of tumor resection surgery. When a tumor in the brain is resected, it can lead to loss of function and can also trigger seizures. The systems I'm building can help mitigate those effects. And towards this goal, I'm envisioning a series of experiments ranging from the artificial models of the brain to ex vivo studies in mice, in vivo studies in mice and swine. This is a long and challenging process, but I've already begun working towards it. I'm a co-PI on a major research instrumentation proposal to lead a series of tapeouts over the next 5 years to build a readily usable BCI instrument. In addition to Yale, I've been collaborating with groups across the country to use their data in designing this instrument and eventually use this instrument to help advance their research on understanding the neural basis of cognition and to build an artificial retina to help restore vision. And I've also been thinking about important systems research to expand the functionality of these devices. I already spoke about how we could leverage techniques from compilers and formal methods to bring more processing power to BCIs. Additionally, we can expand the functionality of these devices by supporting multitasking. Multitasking is important for a couple of reasons. 2 years ago, there was a landmark BCI speech decoding study that was published in Nature. The device that was implanted and used in the study, and the patient who had the device did not have it for speech decoding. Instead, it was there to treat limb paralysis. Because the device was implanted, clinicians with multitasking can reuse that device to discover new algorithms. Multitasking is also essential for clinical applications because it helps treat multiple diseases that can emerge at various points in the lifetime of the patient. But now when we talk about multitasking, We're looking at signal processing that is sharing data and compute with different interfacing needs. Supporting that requires dynamic resource control and understanding interaction between applications. Now, this is at the heart of modern computer architecture design, but supporting it at the constraints of BCIs requires innovation in compute and memory. I've been thinking about how the memory system, for example, can play a key role in supporting multitasking. Now, another aspect of multitasking, as I mentioned, is understanding application interactions. To answer that question of what kinds of applications we want to support, and also to help broadly grow the space, I've been brainstorming with a postdoc at Stanford to develop a standardized suite like MLPerf for the BCI space. This will not only facilitate system design, but will also allow clinicians and neuroscientists to compare the various devices being developed using a common platform. Now, similarly, I've been thinking of research to support cognitive frameworks. I've been working on with a large group of interdisciplinary researchers to integrate my work in a SignLink. Additionally, I'm also looking at ways to expand the Quattro suite of applications, for example, with cognitive models that use both quantum probability and noisy classical dynamics. Now, this is particularly amenable for model architecture co-design in the near term because existing hardware is noisy. I've also been working with Intel to guide the design of future quantum systems based on my research. And all of this is to propel the virtuous cycle of innovation that I mentioned at the beginning of the talk. In the long term, my goal is to build a BCI that can process the terabits per second of data that the brain generates in real time in vivo and interface it with a tiered cloud that can run distributed cognitive frameworks also in real time. This is an ambitious vision, and it might take more than my career to accomplish it. In fact, the work that I've shown you so far is the outcome of collaborations with many individuals across different disciplines and institutions. And of course, many students who are involved in it. But what I hope with my vision and work is to set up a base that can stimulate new research and draw new talent, help nurture new students, such that together we can advance computing, help advance the brain sciences, and importantly, provide a second life to the millions of individuals that need these systems. In this talk, of course, I've not touched upon many aspects of security and privacy and many other questions that need to be answered before designing these systems. One important aspect, of course, which is novel, is to understand the ethical and policy implications of these devices. Last year, a patient in Australia who's been suffering from seizures for 37 years since the age of 3, who began to use a BCI device recently, was forced to undergo explantation because the company making the device went out of business and the hardware and software were proprietary. What could have helped in this case? Perhaps standards for the hardware and software? I do not know the answers to these questions, but I've been working with the Yale Center for Digital Ethics to understand some of these issues and raise awareness. Thank you, and I'm happy to take more questions.
Thank you very much, Raghav. If you have a question, you feel free to just unmute yourself. You could also write your question in the chat.
Hello, this is Ilko Hong in the MSL. Thank you for the good presentation. And I have a simple question. Actually, you like in this example for the actually in the cognitive the work, actually looks like for example, we only get the signal from the brain. We also give to the impact to the brain for giving them some information to the brain, right? So actually that means we can virtualize our the brain with the virtual input and give to the training for in my the brain with for example recognition of flower in this example. They can train then give the input to the brain and they recognize this is a flower kind of thing, right? So
Oh,
actually that means we can also using our brain as some kind of the training or computation machine kind of things. What is this certainly this kind of the work?
Yeah, definitely. You're right in that what a cognitive model is doing is trying to mimic the brain in terms of its learning capabilities. So you can train its inputs, get an output. You can also do the same thing with the brain, and you can perhaps implant memories that way, right? Suppose you want to train something, you could use the brain to do it, or you could use a machine to do it, but imprint those memories to in certain regions of the brain so that you can transfer this. Now, these are some questions, again, which require more research of how we could decode and encode signals into the brain and understand those stimulation patterns. But it definitely is something that can be done. And there are some people who are also looking at, the side effects of doing this. What if, as these devices become popular, we are able to use these devices to falsely imprint memories into people's minds? Now, that would be dangerous, right? So, yes, what you're pointing out is definitely feasible. And hopefully, a lot of rigorous research will go into making that a reality, minimizing the harms that go in that way. Does that answer
Another
your
thing
question?
is,
Mhm.
oh, can I do the one more question? Yeah, actually, in this chips in the implanted in the brain, they may need the power. Actually, how can get the power? Is a battery, or they can some the logics to get power from the our body?
Yeah, that's a really good question. There are different ways that existing systems try to get power. Some use, for example, a chest hub, which has wires that go up the neck muscles to power the devices. Some use like batteries that are implanted forever in the brain. Not forever, like that last several years, like 5 to 10 years in the brain. Some companies like Neuralink are trying to use wirelessly rechargeable batteries. There is, of course, research that is ongoing to harvest brain from the body using glucose cells or temperature differences or the flow of blood in cerebrospinal fluid. But those technologies, today can provide only small amounts of power, like maybe a milliwatt or lower, but they hold a lot of promise in autonomous brain-computer interfaces systems for the future.
Thank you very much.
Raghav, there's a question in the chat
Uh-huh.
from Sean.
Okay. Let me take a look at it. I'm understanding multitasking as using an implant originally developed for one purpose for a different purpose. How does that work? Isn't the location of the implant critical to the task it was designed for? Wouldn't the new task require the implant to be in a different location? Great questions. So, so for the first part, yes, the location of the implant is critical to the task it is designed for. But what happens is, because multiple regions of the brain are involved in processing a task, you can get partial functionality for a task that it was not designed for. For example, in the speech decoding study, the implant was placed in the motor cortex that was responsible for motor movements. But while speech synthesis is not directly about motor movement, if you think about it, we are moving our jaws and our mouth to vocalize our speech. So this particular implant was using that information to decode speech. Later, the authors extended that study where the implant was placed in Broca's area, a region that is responsible for speech, and of course, it gave much better results. But what it showed that is that by enabling the discovery of this algorithm, you could actually test out new speech decoding studies, which of course were then validated with other implants. Now, I would also mention that it's not necessary that we could have very independent kinds of regions in different tasks. Consider, for example, epilepsy and Parkinson's. One might want to measure different frequencies of uh, activity between neurons and stimulate those regions to prevent, for example, seizures in epilepsy, or to treat the motor difficulties that Parkinson's patients have. Now, this again, you could reuse the same implant if it was in a nearby region, or if it was in a region that is connected to it. Because once you stimulate current, it is going to affect the dynamics of the multiple regions of the brain. Does that answer both the questions that you have? Okay, great. Thank you. Thank you. I also see that there's a question from
Yes,
Benjamin.
from Benjamin. Would you like to unmute yourself?
I apologize. I missed the first 45 minutes of the talk. I would love to have a copy of your slides so I could take a look at them for a future reference. I was informed that it looked like you might need quantum machines to do external processing for the brain implant devices. I'm actually kind of perplexed by that because for two reasons. One, I was under the impression that the brain, the neural activity of the brain is not dictated by quantum phenomenon. It's purely classical. And so it's not obvious to me what a quantum sensor could do here. And then the second thing is using quantum computing algorithms to learn about what's happening in the brain is not obvious to me if that is practical to do, because again, the data that we're analyzing, I think, is classical data, not quantum data. So it may not be easily representable using quantum gate operations.
Okay, sure, yeah. So, so I see three questions there, or question comments there. So for the first, I think Rajesh already answered the question that the recording will be available at the Athena site later in this week. The second is about what are quantum systems doing here? Now, in the talk, I described what a computational cognitive framework is, which is a mathematical framework that is used to model what's happening in the brain. So you could think of these frameworks as, behavioral or functional simulators that we use to study computer architecture and system design. And they're not exactly, like if you think of it, these simulators are not exactly mapping, for example, the flow of electrons in transistors, but they are useful to model higher level behavior. And people have been using lots of classical models, Markov models, neural networks, Markov walks, and they've also been using quantum walks because they are more expressive and capture behavior that is difficult to represent with classical frameworks. That is not to say that the behavior of the brain is quantum and so on, but it is to say that this has become an effective tool to represent and assign probabilities. So you could view this as a probability assignment framework that is being used to model behavior. And the reason why we want to look at quantum systems is, of course, the promise of quantum computing is that it can run such kind of computationally hard frameworks faster than classical. So what we wanted to explore is we've studied multi-core CPUs and GPUs for cognitive frameworks. And we also want to look at, in the longer term, as these models become increasingly computationally hard, what kinds of accelerators we would need, and how do we build our system so that one day, if needed, we'd be able to run them, rather than playing catch up where systems evolve and then we are now trying to retrofit our applications onto these systems. And the third is quantum probability a good fit? So I can only give part of that answer because some of it actually has to come from the domain of the cognitive sciences. They've indeed found that it is a good fit. Like, in fact, quantum cognitive models are able to explain human data better than certain classical cognitive models. And I could point you to resources, where there is, I think, deeper questions about the implications of this. So also, there's this distinction between the notion of the brain and the mind. The brain refers typically to the physical substrate, whereas the mind often refers to higher level behavior. So these frameworks are trying to catch the mind while, of course, being connected to the physics, the substrate. So I hope that is, it's a long answer, but I hope that answers all the points you raised.
Yes, it does. Thank you.
Thank you.
Raghav, we have time for one more question. Krishnamurthy has a question.
Yes, thank you very much. This is like an amazing talk. I learned a lot. And I have one first question. Like the processing units that you mentioned are like neural network circuits that are kind of written into like a Verilog code that gets manufactured in the chip.
So we used high-level synthesis to design our processing elements, except for the Fourier transform P, where we got it from the CMU spiral generator hardware generator. So we wrote this in high-level languages, used cadence stratus to give us the Verilog code for it, which we then, take down.
Nice. And then
And this went beyond machine learning, like neural networks. I mean, linear algebra support is only one type. We've had
Yes.
like other signal processing PAs as well.
Oh, nice, nice. And then the second one is it possible to have this implant directly placed on a seizure tumor so that you can actually train the brain to kind of shrink the tumor in one way or the other,
Yeah,
either direct process or indirectly making the brain not supply energy to that region, for example.
Yeah, that's a novel idea. There is a slightly different context in which we've been planning the use of these devices, which is, say, after the tumor is removed, could
Yes.
you use this device to offset that computation? But you could, perhaps think about if you could use this device before and maybe constrict the growth of that tumor, or maybe like not allow it to spread and so on. I don't know, but that is, I think, a new angle that I've not thought about. Thank you.
Great, thanks. Amazing work and all the best.
Thank you. Thank you.
Great. Thank you, Raghav. Would you like to share your email address if anyone else would like to contact you directly with questions?
Oh, definitely. So I'm putting my email address in the chat window, and I really appreciate any both questions as well as feedback on this talk. And thank you so much for the opportunity, and I really enjoyed all the questions. Thank you.
Thank you very much.
Are you a faculty or a postdoc? Or?
I am currently a postdoc and associate research scientist with Abhishek at AL, and I'm looking for faculty positions. So this is sort of my job talk.
Great.
Yeah.
All the best.
Thank you.
All right. Thank you, everyone, for joining.
Thank you. Yeah.
Bye-bye.